If you want to master your NMR problem solving skills, then you are in the right place. Welcome to the NMR Challenges series, where each video presents a new NMR spectroscopy problem from beginner to advanced level. Here, we systematically analyze 1H and 13C NMR, along with 2D techniques such as COSY, NOSY, HSQC, and HMPC, depending upon the problem, to uncover organic structures step by step. So let's get started.
In this video, we will be solving problem number 10 from Pavia spectroscopy book, page number 222. So we have to determine the structure of the compound having molecular formula C5H10O3. They have given us IR spectrum value, which is 1728 per centimeter, depth 135, depth 19 spectral results, and 1H NMR. By the end of this video, you will be able to understand how to calculate the index of hydrogen deficiency, how to interpret 1H and 13C NMR spectra, how to analyze advanced spectra such as DEPT NMR in this video, and at the end, how to collect all the pieces of information logically in order to determine the structure of the compound. In IR spectrum, there is a strong band at 1728 per centimeter. This 1728 value is a characteristics value for carbonyl group, and this carbonyl group can be ketone or aldehyde. If it is aldehyde, so we must see the aldehydic proton in 1H NMR, but there is no aldehydic proton in 1H NMR, therefore we can rule out the possibility of aldehyde, and hence we can say that the compound contains keto group. Now let's calculate the index of hydrogen deficiency. 2C plus 2 plus number of nitrogen minus number of hydrogen minus number of halogens divided by 2. So 2 multiplied by 5 plus 2 plus 0 minus number of hydrogen 10, 0 divided by 2. So we will have 1 degree of unsaturation, and this 1 degree of unsaturation is attributed to the keto group. We have assigned 1 oxygen to the keto group. How many left? 2 oxygen atom left. Now we are going to see the carbon NMR data, which is presented in the tabulated form. We can write these NMR in the graphical form for better understanding. So there are 4 signals in the NMR. It means there are 4 types of carbon, but the compound has 5 carbons. So therefore there is a 2 equivalent carbon, or we can say that there is a 1 pair of carbon. So let's put the 13C in the graphical form. So this signal, let's say, is 25 ppm, this one 55 ppm, this one 104, and this is 204. Signal at 204 is belongs to the keto group, carbon of the keto group. Now we will see depth 135. In depth 135 we have signal in the positive phase. So this signal in the positive phase belongs to the methyl carbon, and we know that the signal in the positive phase belongs to methyl or methane carbon, but the 55 could be the methyl or methane. So we will see the depth 90 NMR, because in the depth 90 NMR we will not see the methyl signal or CH2 signal. We are going to see only methane carbon signal. So if you see, there is no peak, this is no peak, but there is a peak 104. So this belongs to the methane carbon, and of course you will not going to see any peak here. And similarly in the depth NMR you don't see peak at 204, and you are seeing the peak for 104 ppm. So it means the peak at 55 ppm belongs to the methyl group, which is attached to the oxygen. From this carbon NMR we have following information. The first information is that compound have keto group, it has OCH3 group, it has 1 methane carbon and 1 methyl carbon. Now let's look at the 1H NMR. In 1H NMR there are 3 signals, so it means the compound has 3 types of hydrogen, but the molecular formula has 10 hydrogen. So it means the molecule can have symmetry, or there could be equivalent hydrogens. But you have already seen that in the carbon NMR there are 4 carbon signals, right? 4 carbon signals, and molecular formula is 5. So possibility of symmetry you can rule out. It can have equivalent hydrogens. Now let's say this is signal A, this is signal B, this is signal C. So signal A is around 2.4 ppm, which is singlet, and it corresponds to 3 hydrogens. So it is possible that it belongs to the methyl group, and singlet means there is no neighboring hydrogen, and this value 4.2 ppm indicates that the methyl is attached to the keto group. Okay, we get this information here as well, right? So this keto group is attached to the methyl group. Now let's look at the signal B, which is around 3.4 ppm. This is also singlet and it corresponds to 6 hydrogen. Okay, so 6 hydrogen. So possible that there are 2 methyl equivalent methyl group, but this value is very high. So this high value indicates that this methyl is attached to the oxygen, and which we have already seen in the carbon NMR. So from the carbon NMR, we have this information that 55 ppm, the peak at 55 belongs to the methoxycarbon. So there are 2 methoxycarbon for sure. And this is also singlet. So there is no neighboring hydrogen. Now we have third signal, which is around 4.4 ppm. And this is also singlet. And it belongs to 1 hydrogen. So it is hard to say what it could be. But if you remember, in the carbon NMR, signal at 104 ppm belongs to methane carbon. And there is a possibility that this high value, which is 4.4 ppm, maybe it is due to this carbon is attached to the oxygen. So let's put all the information together. The compound have methyl ketone. It has OCH3, 2OCH3 group. It has methyl and it has methane carbon, which is attached to the oxygen. So how many carbons? 2 and 2 to 4, 4, 5, 6. So if you see that you have already combined these informations here, therefore you can remove this one. So what is left? You left with this one, and this one. So 5 carbons are there. Now this is the very crucial part of the structural elucidation. You have to think in a logical way and try to consider all the possible structures and identify the one that is fully consistent with the molecular formula, index of hydrogen deficiency, and all the spectral data. So let's try to draw the possible structure. So COCH3, and now I'm going to put 1 carbon here, and this carbon attached to 3 carbons already is there. So OCH3, 4 carbon, and this is 5th carbon, and in this way you will have CH carbon here, right? If it is the correct structure, then we must be able to assign all the carbons. So this signal will show at 25 ppm. This will come in highly deshielded region, which is 204 ppm. This methoxy will come around 55 ppm, and this is equivalent, so you will see only one signal, and this one will come at 104 ppm. Now you understand why it is coming at 104 ppm, because it is attached to 2 oxygen and further with the keto group. That's why it is highly deshielded, which is almost same to the benzene carbon. So this structure is fully consistent with the 13C NMR. Now let's look the 1H NMR. So I will draw it one more time. So this hydrogen should be A type because it is attached to the keto. It will be singlet and it will be around 2.4 ppm. This methoxy hydrogen is going to come around 3.4 ppm, and it will be singlet as well because there is no neighboring hydrogen, and this is equivalent. So that's why you are seeing the 6 hydrogens. This one is left. So this is C type, which is coming around 4.5 ppm, and it is singlet because there is no neighboring hydrogen. So this structure is also fully consistent with the 1H NMR, and it is satisfying the 1 index of hydrogen deficiency, which is 1, and molecular formula was 3 oxygen. Yes, there is a 3 oxygen. There are 10 hydrogens. Yes, there are 10 hydrogens. And how many carbons? 5 carbons. 1, 2, 3, 4, 5. So there are 5 carbons. Hence, we can say that this is the correct structure for the given NMR problem.
So that's all for today. I hope this video helped to strengthen your NMR skills. Keep practicing because mastery comes with consistency. And I will see you in the next video with the another exciting NMR challenge. Make sure to subscribe so you don't miss it. Till then, take care. Bye bye.